Second.
Hear me?
Second.
Okay.
All right, there we go.
Can you hear me now?
Yep.
Okay, cool. All right, let's see. Last time we were on triangles. This section is quadrilaterals and other polygons. Quadrilateral is exactly what it sounds, a four-sided object. That is a quadrilateral. So is this. Anything that has four sides is called quadrilateral. A polygon is anything that has any number of sides. That's a polygon. So this one is quadrilaterals and polygons. Go ahead and try number one. There's a couple of ways to do this. Most straightforward way would be to just count up the number of squares that are gray. Right?
Mm-hmm.
Well, that would be kind of long and tedious. If I draw a diagonal to that square, which incidentally has 10 columns and 10 rows, so there are how many squares in there if it's got 10 columns and 10 rows?
There's a total of 100.
Okay. So if I drew a diagonal from that point to that point and shaded everything in here gray, what would the area be?
50.
Okay. What's the difference between me drawing this diagonal and what the picture we're looking at? How much more is there in this picture? In other words, we know this is 50, but every square, in other words, there's this part that's additional, right?
Mm-hmm.
And that entire diagonal. So how much extra do we have above 50?
5.
Yes, because we have half of these 10 diagonal squares here. We have an extra half of each. So 10 times a half is an extra 5, so we have a total of 55. What's the sum of the angles of a quadrilateral equal?
360.
All quadrilaterals, yes. The formula for the sum of the angles is n minus 2 times 180. We've done this formula. In other words, for triangles, this gives you 180, which is right. And for quadrilaterals, where n is 4, gives you 360. So that's the key here. We know that the sum of that angle, that angle, that angle, and that angle is 360. Remember, with these geometry problems, you always have to do something else first before you can figure out what x is. What's this angle right there?
That angle.
Remember, whenever you have a straight line and something intersecting with it, angle 1 and angle 2 are always supplementary. So they always add to 180. So what'd you say it was?
125.
How about 105?
Oh, yeah, 105.
There is one skill in geometry that is going to benefit you tremendously. And that skill is being able to subtract a number from 180. In other words, that is a thing that you have to do over and over and over, is subtracting numbers from 180. Because there are so many numbers that add to 180, and they always give you either one or two of them, and you have to come up with the third one. So what's this angle right here?
20.
120, okay. Now we have three angles in our quadrilateral, and we can figure out the fourth. What's the fourth going to be? It's the sum of these three here.
The sum of them is 275.
Okay. We're subtracting that from what?
360.
Okay, what's that difference?
85.
You got it. Hold on. Here's a pentagon. Now, just a note on terminology. Pentagon just means 5 sides. Okay? A regular pentagon means 5 equal sides, 5 equal angles. In fact, a regular polygon means all sides are equal, all angles are equal. So you have a regular hexagon, which is 6 sides. This is just a polygon, a pentagon rather. Pentagon meaning 5 sides. What's the sum of the angles of a pentagon?
360.
Remember, that's the formula for the sum of the angles. It was 360 for a quadrilateral. This is a pentalateral, or a pentagon. So substitute 5 for n. What do you come up with?
3.
So 3 times 180, which is 540. In other words, every time you pick up a side, you pick up 180 degrees. When I go from 5 to 6, it's going to go from 540 to 720, and so forth and so on. So every additional side adds 180 degrees to the sum of all the angles. So what equation can I write for this pentagon? What has to be true? These little things here mean 90-degree angles.
So 300 plus 2x equals 540.
Where'd you get 300? You're close.
All right. I added 90 to...
90 to 90 is 180. But then 180 to 130 is 310. So 310 plus 2x equals 540. Next step.
Subtract 310.
So 2x equals 230. X equals...
Oh, sorry.
That's all right.
The little thing that...
Just seeing how good you're going to do these in your head.
115.
All right. They want the ratio of the area of this triangle to the area of the entire square.
One third or one half.
One half. And let's talk about that a little further. It doesn't matter if this is a square or a rectangle. It could be a rectangle. Hold on. If you take a rectangle, what's the area of a rectangle?
Base times height.
Okay. And if I draw a diagonal through it to create that triangle, what's the area of a triangle?
Base times height divided by 2.
Right, 1/2 base times height. So as long as I do it this way, it's clear that the area of this triangle is half of the area of the rectangle. Well, it turns out that it doesn't matter how I draw that triangle. I can draw the triangle like that. What's the area of the triangle? Always?
1/2 times.
And it's always vertical height.
Oh.
So the area of this triangle must also be 1/2 the area of the rectangle, right? And even if I draw the triangle like this, as long as that vertex is along the top, well, I know the area of this triangle is always 1/2 base times height. Therefore, no matter how I draw that triangle inside that rectangle, it's half of the area of the rectangle. The fact that this is a square, well, a square is still a rectangle. In other words, the area of a square is still base times height. It's just that the base and the height are the same thing. But it's still base times height. All right, let's go on. I think that's the last page here. We want to go to 162. This is also a polygon, but this looks like a 1, 2, 3, 4, 5, 6, 7, 8-sided polygon. So we have to figure out, what's the first thing we need to figure out here?
Length of the top of the T.
Well, we need to figure out the area of this polygon, right? In other words, we're going to code it in tiles, and we know how much the tiles cost for 1 square meter of tile. So if we can figure out how many square meters of area there is in this thing, then we'll just multiply however many square meters we have by $2 for each square meter, and we'll know how much the cost is to tile. So, and this whole thing is 16. How are we going to figure out the area of this object?
Not sure.
Well, we want to break it up. You can always arbitrarily draw lines. So I'm going to draw a line there. Now, instead of having an octagon, I've got 2 rectangles. Well, what's the area of this rectangle right here? What's its height?
12.
Uh-huh. So what's its area?
36. No, not 40, 36. Well, 48. I don't know why.
It's all right. So that's 48. What are the dimensions of this thing here?
I don't know the length.
Well, it's 16 from here to here, and it's 4 from here to here. So what is it from here to here?
Oh, so 12.
Yeah, so that's also 12 by 4. So that's another 48. So how many total square feet do we have? Or square meters, excuse me?
96.
96 square meters. We are multiplying that by $2 per square meter. And it's always a good idea to make sure your units cancel. In other words, this square meter in the denominator cancels with that square meter, and I get 2 times 96, which is $192. If your units don't come out properly, then you've probably done some mistake. You've either multiplied when you should have divided, or the other way around.
Yeah.
Huh. Oh. Number 6. Here, let me lengthen it. What do you have to do here?
Mm-hmm.
I said, what do you have to do here? First of all, you know the definition of area, and the perimeter is just the distance around. Perimeter is like circumference for a circle. We know that the total area of all 5 squares is 20. Our goal is to figure out what x is. Once we figure out what x is, then we'll be able to figure out what the perimeter of this figure is. So, if the total area of the 5 squares is 20, what's the area of each square?
4.
What's x?
2.
What's the perimeter?
24.
Good. It's fast. Did you do it like this? So there's 6, and then 6 more, 6 more, and 6 more. Is that the way you did it? How'd you get 24 so fast?
What I did is I counted the amount of sides that were on the perimeter, so then I got 12, so I just did 2 times 12.
Okay. Yeah, that's basically that way. Yeah. In other words, we're not going to count these inside squares because they're not on the perimeter. So you could actually done the perimeter of each one times 5 minus 4 of perimeters. But there's lots of ways to think about it. But let's see, is that the last question on this page? I think it is. Go to intermediate. So if this is rectangle A, the length of A is 1/2 the length of rectangle B. So rectangle B is going to look about like that. And the width of A is 1/2 the width of B. So this is rectangle B. It's the ratio of the area of rectangle A to the area of rectangle B.
Double?
No,
So, 2 to 1.
no, it's not double. Visually, what does it look like? I tried to draw these to scale. How many of rectangle A's will fit inside rectangle B? What's it look like?
6.
Yeah, 4. Okay. Let's look at rectangle B. Rectangle B has a base of B and a height of H. What's the area of B?
CH.
Rectangle A has a base that's half of this and a height that's half of that. What's the area of rectangle A?
1/4 BH.
Right, 1/4 BH. So the ratio of rectangle A to rectangle B is 1/4 BH over BH, which is 1 to 4. And this is true no matter what object you're drawing. In other words, if, say, I had a circle that had a radius of 2 and another circle that had a radius of 4, well, this is pi r squared, so that's 4 pi. But this is pi r squared, that's 16 pi. So when you're looking at what I call the linear dimension, which is radius, or in this case, either the base or the height, but that's a linear dimension. That's one dimension. And when you go to a different object where the one dimension ratios are 2 to 1, the area ratios are always going to be the square of that. Okay? So let's assume that it was a 2 to 6 linear ratio. In other words, this circle has a radius of 2, this has a circle a radius of 6. That's a 3 to 1 linear ratio, but this ends up having an area of 36 pi compared to 4 pi. That's 9 to 1. So when you go from linear to area, your ratio of the areas is the square of the ratio of the linear. In other words, you go from a 3 to 1 linear ratio to a 9 to 1 area ratio. Let's make it 5. What's the linear ratio? Circle B, the big circle to the little circle. What's the linear ratio?
2.5 to 1.
Well, 5 to 2 is the simplest way to put it. Right?
Mm-hmm.
In other words, one's radius is 5, the other's radius is 2. That's a 5 to 2. And notice that radiuses are measured in inches or meters. So anything that's measured with a singular thing like that is a linear measurement. as opposed to an area measurement, which is always square meters or square feet or square inches. Well, what's the area ratio? If my linear ratio is 5 to 2, and my area ratio is the square of the linear ratio, what's the area ratio?
1 to 4.
25 to 4.
25.
Which is like more than 6 to 1. So it goes up big time. And then when you go from 2 dimensions to 3 dimensions, it's the cube of the thing. In other words, let's go back and look at our squares. If this is 2, and this is 4, and this is 4, my linear ratio is 2 to 1, correct?
Mm-hmm.
My area ratio is 16 to 4, which is 4 to 1. And my volume ratio is going to be the cube of the linear ratio. It's going to be 8 to 1. The volume of this thing is 4 times 4 times 4, 64. So 64 to 4 what did I do? I made a mistake somehow.
Mm-hmm.
What my volume ratio should be 8 to 1.
Volume ratio?
Yeah, and it is. Notice the volume. Yeah, I know where I went wrong. The volume of this little cube is 2 times 2 times 2. So this volume is 8. This volume is 64. So the volume ratios went up to 8 to 1, which is the cube of the linear ratio. And this is an important concept in geometry, is that every time you go from a singular measurement to an area, you square the ratios, to a volume, you cube the ratios. And this is always in cubic feet or cubic meters. And you can write that as feet cubed if you want. This is always in feet squared, and this is always in feet. And it doesn't matter whether we're talking cubes, rectangles, spheres, circles, polygons. It's true across the board.
All right.
That as that linear ratio, whatever it is, the area ratio is the square of that, and the volume ratio is the cube of that. All right, that's a good place to stop.
All right.
Cool, have a good week. I'll talk to you next Monday.
Talk to you next Monday.
Bye-bye.